electron volts, and you have to convert that to joule, and 1 electron volt is that many joules per electron volt. So that's the conversion factor. The mass of the electron is, this is the electron mass, 9.11 times 10 to the minus 31 kgs. Right, so this comes to the top, then that becomes 12. 12 and 3 is 15, and we'll make that 16. Square root of 16 is 10 to the 16 is 10 to the 8. So yeah. So V is 10 to the 8 and in the you have 2 times 4 times 1.6. Divided by 9.11. What had this number better be?
Positive.
Okay. What is the speed of light?
Oh, less than the speed of light.
Yeah, so this speed of light is 3 times 10 to the 8, so this number had better be less than 3. Yeah. All right, so you see, you speed up an electron using 40,000 volts, and you can get to a third of the speed of light. That's what it's saying. Okay. And then you hit the electrons against a wall or a heavy metal, and all that kinetic energy gets converted to X-ray. This problem says find the maximum potential difference between 2 parallel conducting plates separated by 0.5 centimeters of air, given the maximum sustainable electric field strength is 3 times 10 to the 6 volts. Okay. So again, this is 2 conducting plates, and this is a parallel plate capacitor. Okay. And they're asking you what is the potential difference between the plates, and you saw that this is equal to the electric field times the distance. So there's a maximum value of electric field you can have. If the electric field exceeds that, then this air becomes conducting. It'll spark and the charge will discharge. So the maximum electric field gives you a maximum voltage to which you can charge. Okay? So V max equal to E max times D. E max is 3 times 10 to the 6 volts per meter. So that tells you the maximum voltage, maximum energy you can store in the capacitor. 0.5 centimeters. 0.5 centimeters is 5 millimeters, about that thick. Okay? So the maximum voltage to which you can charge this capacitor is, so that's 10 to the 4, and that's 1.5. So 15 into 10 to the 3 volts, 15,000 volts. Okay. Are you guys familiar with cylindrical polar coordinates? Okay. Spherical polar coordinates. Okay, you're all familiar with this guy. These are Cartesian coordinates. All right. So you use different kinds of, why do you use different coordinate systems?
For different, different planes. So like you have XY, which is basic, and then you have XYZ. Or actually, wait, no. XYZ is, like squares or something like that, and then you have spheres, and then you have cylindricals. You
Yep.
have a sphere, and then you have a.
So if you want to do an integral of, if for this cup, which without this handle, this has cylindrical symmetry, and then you want to use cylindrical polar coordinates, okay?
It's for integrating.
Yeah, or any kind of, you can be solving differential equations and all that stuff. Okay. If you want spherical polar coordinates, then it has to be, you're doing integrals for spheres, like football and stuff like that. And this is when you don't have any symmetry. Okay? So for instance, if you were doing an integral for a basketball and you did it in these coordinates, the problem will be very hard. It's like trying to talk Hindi in South America. Okay, that's not good. Okay, in South America, you want to speak either Spanish or Portuguese, or something like that. Okay, so here's a problem that has cylindrical symmetry. So this is the coordinate you need to use. Okay. Yeah. So they're using S for that radial coordinate, so we'll say S. Okay. So what this is telling you is, so I'll draw a coordinate system. So here, again, we reference everything to the Cartesian coordinate system. Okay, so in this system, S is this distance, that's S. Theta is this, and Z is that. So the coordinates of this point are S, theta, and Z. Okay. The coordinates of any points are specified by 3 numbers. You can give the coordinates of this point either in this language, or that language. The coordinate of any given point can be given in terms of any of those. Which language contains the most information?
They all contain the same, right?
They all contain the same information. So there will be rules for interchangeability. Okay? All right. Infinitesimal distance in this coordinate system, we'll say, this notation is crazy, is ds and s hat. S hat is a unit vector in the radial direction, so this is the small distance you travel in the radial direction, plus s d theta, theta hat. Okay, s is how far you were and how far, through what angle you turned, small angle you turned along that direction. Okay, so you went this distance along that direction, and then this distance along that direction, and then this distance along the z direction for this infinitesimal distance. Okay, that's the small distance traveled in cylindrical polar coordinates. Okay? All right, so this tells you the electric field in a region is pointed away from the z-axis. So electric field is always pointing away from the z-axis. The magnitude of the electric field is given by E equal to alpha divided by S. So the electric field, as you go further and further away, it's becoming smaller, but it's always pointing away. So here, okay. So the electric field is given by alpha S S hat. Okay. They want you to find the potential difference between P1 and P2. P1 and P2, explicitly stating the path over which you conduct the integration. All right, I'm going to write this down. So V final minus V initial, and you can look at your notes, is this line integral from the initial to final point, E dot dr. Okay. What kind of field is an electric field? I'm sorry?
Vector field.
It's a conservative vector field. What does that mean? It means that this line integral is independent of the path. Okay? So in this problem, you can go from here to here. In which way? You can go along that path, along that path, along this path, and that value of the integral will be the same. Mm-hmm.
You have to go around because the field's always pointing away from Z, right? That's why so you have to go around.
Oh, no, what I'm saying is you can go from here to there in any way. You can go like that.
Oh.
The integral is independent of the path. So you choose the wisest path. You choose the path along which you can easily do the integral. Okay? And it turns out that path will be the following. It'll be this path plus this path. We'll call the first portion 1, the second portion 2. You'll see in a second why. Okay? All right, so that integral is along path 1, E dot dr plus integral along path 2, E dot dr. Okay, along path 1, and I'm using funky notation. Actually, I'll write path 1, that's a better notation. Okay, what is E? E is alpha S hat over S. What is dr? Dr, only theta is changing along that path. Only this guy is alive. Okay? So it is S dot d theta, theta hat. What is S hat dot theta hat? What is I dot j? I dot j. I cross j is k. These are mutually perpendicular unit vectors. 0. Theta hat is a vector along the curve. S hat is a vector perpendicular to it. So that vector and that vector, they'll always be 0. So the first integral is 0. That's why we chose that path. Okay. Plus the integral along the second path, E dot dr. I'll write that in a second. So this guy is 0. So now this is equal to integral along the second path. What is E? E is again alpha S hat S. Now along the second path, see, you're going along this path. Only this guy survives. D theta is not changing and dz is not changing. So it's ds S hat. And S hat dot S hat is what? I dot I is what? I dot I is 1. J dot J is 1. K dot S is 1. Okay, so this is equal to minus alpha ds over s. Okay, and from the initial radius A to B, this is the initial radius is A, S to B. So V final minus V initial is minus A to B alpha S ds. Okay, and even I can do this integral. This is just log S minus alpha is a constant, log S B to actually, no, we'll write it like this. Okay. Okay, V final is that radius, so minus alpha b. At a given location, the potential is, so what this gives us is Vs, the potential at that is minus alpha log s. That's what the potential energy function is. Okay.
So, wait, what was the final answer?
Yeah, this one is the final answer.
And you want us to write it like that with the natural log split up,
Mm-hmm. Well, you can write it,
either way?
yeah, you can write it like this. You can write it like this. I just wrote it like this, so now you could see that this was the final point. B was the radius at the final point. This was the radius at the initial point.
Okay.
Yeah.
Can you go back one slide for like 30 seconds?
In nuclear fission, a nucleus splits roughly in half. So in a nuclear reactor, you're taking a heavy nucleus, and all the nuclear reactors that we have now mostly operate on U-235. That's the nucleus you're splitting. How do you split the nucleus? You shoot a neutron at it. The neutron gets absorbed, and this becomes unstable, and it splits into two chunks, roughly half up, roughly down the middle, and then 3 more neutrons, and then these guys cause further reaction. And then you get energy. Okay. Why do you get energy? When do you get energy? So this is at the heart of the matter.
The mass of the resultant particles is slightly less than
Very good.
what you started with.
So when the mass of the products is less than the mass of the ingredients, that's when you get energy. Okay, so when you burn wood, oxygen and wood combine to give you ashes, carbon dioxide, and water vapor. The masses of the product has to be less than that to get energy. Okay, the number of neutrons and protons here is equal to the number of neutrons and protons here. So why is the mass less?
Doesn't it take energy to keep the bigger particle together? 'Cause there's more
Like,
mass.
aren't those energy levels, if they're broken, it has to go somewhere, so it's kind of given away.
Okay, so we'll understand this. Okay, so here's an electron and a proton. I mean, these are rough numbers. If the electron weighs 1 unit, this guy weighs 2,000 units. Yeah. Here's an hydrogen atom. What are these circles?
Energy levels.
Energy levels. Okay. So I take this electron and proton, but I need more room. So okay, this is the last problem we'll do. Okay, so there, ionization energy of hydrogen from the second level is 3.4 electron volts. All right, so you go to a store, buy these two particles. This guy weighs 2,000 units, this guy weighs 1 unit. I'm just making up numbers. And you make a hydrogen atom out of it and put the electron in that level. Okay, now they have formed a bound state. They have attracted each other, formed a bound state. And whenever they form a bound state, this guy weighs less. This guy will weigh less by 4.3 electron volts. That's how much he will weigh less. If you take the same two particles and make the hydrogen atom there, this guy weighs 13.6 electron volts less. Same number of particles. The tighter something is bound, the less it weighs. Mm-hmm.
Would the first one be unstable? Like, how is it able to maintain that at
Yeah,
the
yeah.
second?
Yeah, it'll be unstable. It'll move to the ground state. But the point being made here is the tighter something is bound, the less it weighs. All right, coming to here, same number of neutrons and protons. If these guys weigh less, that means these guys are more tightly bound. Protons and neutrons are most tightly bound in which nucleus? Iron. So, in fusion reaction, you can go up to iron and release energy. In fission reaction, you can go up to iron and release energy. Okay? So you're releasing energy. And the energy released per reaction is about 200 million electron volts. Okay, so that is the that's why we love nuclear energy. Okay, in nuclear fission and nuclear splits nearly in half. What is the potential? So these guys, when they split, the potential energy when they're this close apart from a fragment that has 46 proton in it. Okay, what is the electric potential at this distance? So here's this proton, the charge is 46e, and the potential kq divided by r. Okay, so okay, that's 10 to the minus 5 and 10 to the 4. So the electric potential from one fragment, one large fragment, is 9 times 46 times 1.6 divided by 2 into 10 to the power 4 volts. .31 into 10 to the 6 volts. So right next to one fragment, the voltage is 3 million volts. Okay. What is the potential energy in MeV of similarly charged fragment at that distance? So now you have two particles. The potential energy is K Q1 Q2 divided by R. So it's V times Q2. It's 3.31 times 10 to the 6 volts times 46 times 10 to the minus 19 coulombs. And that works out in joules, so $152.3 into 10 to the minus 13 joules. And so this potential energy 152.3 into 10 to the minus 13 joules, and we got to convert it into MeV. 1.6 into 1 MeV is 1.6 into 10 to the minus 13 joules. So just the potential energy between these two fragments is 100 million electron volts, and then you have the energy of these guys. Okay, so that's the energy that's released in a fission, which gets converted to heat, which you use to boil water. Okay.
Back to